So we're going to talk about Kepler's first law now. We're not doing them quite in order. It's called the Law of Ellipses. When Kepler analyzed Tycho Brahe's data, he came up with 3 laws, and the first one was that the planets travel in ellipses rather than in circles. And this is the really huge philosophical break that Kepler was able to make that sort of broke the back of this problem. And so Newton wanted to be able to derive this, and there's a whole drama that went with that during Newton's lifetime. He wanted to apply his laws and his law of gravity and show that Kepler's laws were a subset of that. And so here we are, we just did the second law, here we are doing the first law. And we're going to begin with agreeing that, that we're going to just talk about central forces, or forces from a central potential energy. And so that means you have a force coming from a single point in the center, and your satellite is orbiting somehow that point. And so what that means is that, in our case, the force is attractive. The force is along the line connecting the object to the center. And so that has some consequences. For example, there can't be any transverse acceleration. There can't be any acceleration in the forward or the backward direction. It can only be on the line of the direction of the force because of Newton's second law. And so you can rewrite this way and say, look, I have some force function which only depends on little r, not its direction, because all that matters when you have a central force is how far away you are from it, not which angle you're at. And that's equal to mass times the acceleration, which we'll write this way to call back to chapter 1. And so we're going to come up with some equations for this. If you go back to chapter 1, the acceleration in polar coordinates, and that's how we're going to solve this, had sort of 4 terms, you might say 2 terms, but each had 2 pieces to it. And so there was a radial component, it's multiplied by E hat r, and a transverse component multiplied by E hat theta. So for central forces, this guy has to be 0, because there's no speeding up or slowing down of this particle. It's being just affected by the point at the center. It's only along the line. And so this is the acceleration of the particle into central force. And so this is the one we're going to plug into that equation on the next sheet. So we'll go to that. So our equations of motion are then reduced to this. Here's the radial part, and here's the transverse part. We get m times r double dot minus r theta dot squared equals f of r, and m times 2r dot theta dot plus r theta double dot is 0. This is the transverse piece, this is the radial piece. We can do a little algebra on this one and see that really this is just d by dt on r squared theta dot if you factor out an r. And so I can replace this with d by dt on that. And what that means is that this derivative, this quantity has to be constant for the time derivative to be 0. And so this is back to sort of an angular momentum statement. R squared theta dot has to be a constant. It turns out it's equal to the angular momentum divided by the mass. And we'll give that a name. We'll call it little l. Little l is the angular momentum per unit mass. And it's just r cross v instead of r cross mv. And so ultimately what we want to do is solve these 2 differential equations, and then we can plug in a force, like a 1 over r squared force, or 1 over r cubed force, or something like that, and see what orbits we get. When we start this, we'll be just looking for the shape of the solutions in r and theta, and not worry about the time variation. In other words, we just want to get a shape of the orbit out of this. And so I'll be making some substitutions. For example, I'll be saying r equals 1 over u, and then I'll substitute that in and solve, and we'll put these differential equations in a form where we can see solutions that give us the shapes of the orbit. What we're looking for is an ellipse. So we've reduced our orbital equation to these 2 differential equations. This is the one that is sort of telling us that the angular momentum is constant, and this is going to give us the relationship between radial position and angle. So we'll get the shape of the orbit out of here. Of course, we haven't specified that the central force is 1 over r squared, and so this is pretty general, as long as you have 1 over r squared force. We can put any function of r in there we want. And so the first thing we're going to do here is eliminate time. And so we're going to end up ultimately with a solution in r and theta, which will give us the shape of the orbit. And so we do that, we eliminate time by doing this substitution. We replace r with 1 over u, and that gives r dot is minus 1 over u squared du dt. And then we're going to use the chain rule on that. And we're going to say, write that as du dt is du d theta dt times minus 1 over u squared. D theta dt is theta dot. And so r squared theta dot is just L. And so notice we don't have any time dependence anymore because the angular momentum is constant. And this is the angular momentum per unit mass, right, is constant. And so that gives us r dot. And then we're going to take the derivative of that with respect to time. And we're going to use the chain rule again. And we're going to say d by dt is d theta dt times d by d theta. And so this is going to give us r double dot, which it looks like this. It's minus L theta dot. The theta dot comes from this term. Times d squared u d theta squared. So it's now, instead of a second derivative in time, it's a second derivative in theta, our differential equation. And then we can look at this theta dot and rearrange it so that it's just another angular momentum term. Remember, the angular momentum per unit mass is r squared theta dot, and so it's the same thing as theta dot over u squared, and so theta dot is u squared times the angular momentum per unit mass. And so I can take this piece and stick it in here for this one, and that gives me an r double dot that also has no time dependence. It rearranges to this. And so now equation 1, which looked like this, now looks like this. It's got this r double dot term, and it's got this r theta dot squared term. And that depends on f of r, which is f of 1 over u. And so now we've got a differential equation in u and theta, and whatever our force is, and it's got no explicit time dependence. And so we're going to do various things with this. So this is what our differential equation looked like that relates position and angle. Again, r is 1 over u, so position and angle to the force. And if we just do a little math on this and rearrange it, it looks like this. We just divide through by ml squared u squared, and it gives us a differential equation that looks pretty simple. It's the second derivative of u with respect to theta plus u, gives you the force function over ml squared u. And so your book has an example, a few examples, but I'll just talk about one of them. In this example, they say, look, the radius is related to the angle by this formula. C is a constant, and so r is equal to c theta squared. And so this is an outward spiral. As theta increases, r goes as the square root of theta, and so it spirals outward. And so we can rearrange this to give u instead of r, and since r is just 1 over u, u is just 1 over c theta squared. And what they're asking us is to use this to determine f of r, right? So we can take the second derivative of u with respect to theta, add u to it, multiply it by this quantity, and get the force function. And so that's what we do here. First we calculate du d theta, and it gives us this quantity. If you take the derivative of this with respect to theta, it's straightforward. And the second derivative with respect to theta is this quantity, right? It's just another straight derivative. And you can rearrange that to, since u is equal to 1 over c theta squared, you can solve for theta squared, or theta to the minus 4 in this equation, and substitute, and you get 6cu squared is the second derivative of u with respect to theta squared, with respect to theta. And so then this equation here can be written this way: cu squared plus u, so the second derivative of theta, right? The second derivative of u with respect to theta plus u is equal to this quantity. And so you solve for the force function just by multiplying through, and this gives you the force function is minus ml squared times these two. And then you just substitute in r for 1 over u, and you get the force function as this. And so what this is saying is that this force function gives you an outward spiral. And so if you could create this force, you could produce orbits that spiraled outward. Okay, that's just an example of using the orbital equation. So now we can begin to ask the question, what happens for an inverse square force? Here's our differential equation for the orbit. And an inverse square force is just k over r squared. This could be GMM or kqqq, for Coulomb force or something like that. We're just putting a minus sign on it to call it attractive. And so if I write it in terms of u, it looks like this. And so it's minus ku squared. The minus signs cancel. And I get d squared u d theta squared plus u is equal to k over ml squared. Looks like this. And so this should look familiar to you from our harmonic oscillator type problems. If it was 0, this would just be sines and cosines. But instead, it's got this kml squared, which is all constant, right? L is the angular momentum per unit mass, m is the mass, k is just whatever the coefficient is for the 1 over r squared. And then so when I take the second derivative of u, this piece goes away, and I just get the negative, the cosine, and the u will carry this term, which will cancel that term, and so the whole thing will be 0. And so this is 1 over r, and so r ends up being 1 over this whole thing. And then a and theta naught are determined by initial conditions. And so we'll work with this solution a little bit. So this is a GeoGebra view of the solution to the orbital equation. If you look over here, this is sort of the general form of the orbital equation, b over 1 plus a cosine theta minus theta naught. Now, the b is really ml squared over k, as in the notes, and the a has the ml squared over k constant built into it, but it also has a coefficient which we actually called a in our notes, and it's got this initial angle. And so I'm just going to show you what the solutions look like graphically to this equation for various values of what I've used here as a, b, and theta naught. And so if I set a equal to 0, which is right about, here, this becomes a perfect circle. This is the equation for the radial position, right? And if a is 0, then the radius is just b, right? Independent of theta. And so you can see that if I scale b up and down, if b is 2, then the radius is 2. If b is larger, then the radius is larger, and so on, right? And similarly, if I go the other way, it's a little weird if I make it negative, but really I'm just talking about the magnitude of this. And so I get circles for the case where a equals 0. And so now let's pick a value of a that's like something different from 0. And notice here's where I start getting an ellipse, right? And so the more I make a close to 1, the more elliptical I get. If a gets to 1, the orbit is actually parabolic. And I'm going to show that by shrinking b back down. So b, I'm just going to scale the whole thing down a little bit. And now let's look at what happens when I increase a, and you can see, so right about there, when a equals 1, this thing becomes parabolic. And like I said, b just scales it down. So let me just go back to an elliptical orbit. So a parabolic orbit is also a solution for this, not just ellipses and circles. And you can kind of see, here's an ellipse again. And so you can see the center here is one of the foci, right? I'll make it a little bigger. And now let's vary theta naught, right? What theta naught does, let me get rid of that. What theta naught does is just change the orientation angle. And so usually we're not that interested in that. We don't care what the initial angle is. We just care that what the shape of the orbit is. And so usually you'll see in most of the problems we do, theta naught is just set to 0. It doesn't really matter. It's just you can have any orientation for that orbit. And so now let me go back to the a. So I said when a gets up to 1, the orbit is parabolic. And then beyond that, it's a hyperbolic orbit. And so you can kind of see as I get to larger and larger values of a, the orbit becomes a hyperbola. And so all of these things hyperbolas, parabolas, ellipses, and circles are all legit orbits for the solution to a central force that goes as 1 over r squared. And these are called conic sections, and these are what Newton discovered would be all the allowable orbits for objects in orbits if the gravitational force goes as 1 over r squared.